Hello, everyone. Welcome to Robotics Today. It is my pleasure to introduce Koushil Sreenath, our speaker today at the series. Koushil is an assistant professor at the Mechanical Engineering Department at UC Berkeley. He got his PhD and master's at the University of Michigan, and after a postdoc at the GRASP Lab, he started his faculty career at Carnegie Mellon University. Koushil directs the Hybrid Robotics Lab, where he studies the control of agile and dynamic motions in hybrid and underactuated machines like legged and flying robots. So as you can imagine, his research is not only academically impactful, as one can see from his NSF Career Awards, RSS Best Paper Awards, Google Faculty Awards, but it's also very visually appealing, you'll see, and has been featured in media multiple times: Discovery Channel, CNN, ESPN, Fox, CBS. They can't get enough out of Koushil's research. So Koushil, we're all eager to hear and see what you have to say. Welcome to Robotics Today, and thanks for taking the time.
Thank you, Alberto. This is my honor to be on this. Thank you for having me. So let me share my screen, and hopefully this works. All right, so let me get started. So I wanted to talk a little bit about safety critical control for dynamic systems. And I wanted to do a model-based and a data-driven approach, so the combination of the two. So before I get started, I wanted to acknowledge the many collaborators as well as the funding sources without whom this work is hard to do. And more importantly, I wanted to acknowledge the students, and they're the ones who do all of this work behind the scenes, and I get to showcase their work. As a tribute to my students, as I was making this talk, I realized I have some amazing students. I decided to use slides just from the students. So what you're going to see are slides that are created by the students for their talks. So I'm stealing their slides entirely, and I'll be talking about them. If I make any mistakes, they're probably mine. All right, so let's get started. Here's the outline of my talk. So what we're going to talk about today. So we'll start with model-based controls. So we'll look at control Lyapunov functions as a way of stabilizing equilibria, either static points or periodic orbits. Then we look at control Lyapunov function-based quadratic programs as a way of enforcing stability, in addition to constraints, input constraints, force constraints, and so on. Then we look at safety critical constraints, which are then enforced through control barrier functions based quadratic programs. Then we'll introduce model uncertainty. Now, once you have model uncertainty, there are techniques in the model-based control community to address this. But instead of doing this, we'll switch all the way over to the data-driven approaches. So we'll use reinforcement learning, and we'll see if you can throw away all the models and still make things happen. But then you'll lose some guarantees, and then we'll try to find a middle ground. So we look at reinforcement learning-based CBFs, CLFs, and then we look at Gaussian process regression-based CBFs and CLFs. So that's where we are headed in the next 45 minutes. Now stay buckled up in your seats. Let's start. So control Lyapunov functions and control Lyapunov functions-based quadratic programs. So we'll start with control affine systems. X dot is f of x plus g of x times u, our favorite systems. So these systems have a drift vector field, a control vector field. And most dynamical systems can be represented as these affine systems. In particular, the SCSI cal that's shown over here is also a control affine system. The goal is to design a controller to stabilize the system. And if you're talking about stability, the first thing that you should think about is Lyapunov functions. These are the gold standards to provide guarantees and stability. So here's a cartoon. So on the bottom, we have the state space. And the goal is to reach this equilibrium XE. So if I start at a particular initial condition on my state space, my V of X is over here. And as I evolve along the trajectory, I go along this, my V keeps on decreasing. And this happens as long as for all states in my state space, I can find a U that can ensure V dot is less than 0 for all points other than X equilibrium. Now, if such a V exists, then my system can drive states to my equilibrium. So if we want to, what we want to look at next is we want to look at more stronger notions of stability, not just asymptotic, but exponential. And to do this, we want v dot plus a constant times v to be less than or equal to 0. So this ensures that wherever you start, your state evolves in such a manner that you're always upper bounded by this decaying exponential, which is given by v dot is equal to minus lambda v. So your state can evolve anywhere below this. And eventually, as t goes to infinity, you reach exponentially fast to your equilibrium. So this is the exponentially stabilizing control Lyapunov function. And this constraint is something that we'll keep in mind. If I look into v dot, so v dot is nothing but the gradient of my Lyapunov function times my dynamics x dot. X dot is control affine. So then I can write down v dot as the gradient of v times f plus the gradient of v times g times u. So this is your Lie derivatives LFV plus LGV times u. The key thing here is v dot is control affine. And we'll achieve a few things from this property. All right, so one particular control that can achieve this constraint is the min-norm control. This goes back all the way in the history to the 80s from Artstein and Sontag. So we want to choose the smallest u that can enforce this v dot plus lambda v is less than or equal to 0. So suppose I define psi 0 and psi 1 as these quantities. So I'm taking LFE plus lambda v as psi 0, LGV transpose as psi 1. So this constraint that I want to enforce basically boils down to this constraint. Psi 0 plus psi 1 transpose u should be less than or equal to 0. Now, one control that enforces this is the following. If psi 0 is already less than or equal to 0, then I pick a u that does nothing, u equal to 0. Only in the case psi 0 is positive, then I pick the smallest u to make this entire thing equal to 0. So this is the min-norm control. And what it essentially does is the smallest amount of control effort to stabilize your system. If your dynamics are already stabilizing without your control input, your controller takes that into account. So this is pretty cool. What we found out is this exact controller is equivalent to a quadratic program. And this opens the door to lots of different types of controllers that we can do. So let's see what this quadratic program is. So if I were to formulate a quadratic program where I'm minimizing u transpose times u, so h equal to identity, subject to this exact constraint corresponding to the exponentially stabilizing control Lyapunov function, the solution I get is the min-norm control. But now I can run this online in real time. So we have QP solvers that can do the things really fast. But then you can add in more things. So once you have a QP, you can add in things like an input constraint. Now, if you have multiple constraints, then you need to relax the CLF constraint and penalize the relaxation. Now here's a CLF QP control, the very first one in action. And turns out I ran this experiment remotely, although this is way back before the pandemic. We're still looking forward to preparing for it. Running experiments over Google Hangouts from 600 miles, 1,000 kilometers away. Works on hardware, enforces degree stability, and also enforces torque constraints. Okay, so let's step up a little bit more. So we've seen control Lyapunov functions and based as quadratic programs that can give you stability and constraint enforcements. Let's look at control barrier functions as a way to give us safety critical constraints. So what's an example of a safety critical constraint? The classical example for legged systems is to walk on this terrain of stepping stones. So you and me, we've probably done this as kids quite well. This kid is pretty good at it as well. You get on his last step, actually does nail stepping on the stepping stone. It's just that it fails to account for the contact forces. So there's a thin film of water on which he slips. So if you have to make this work on robotic systems, you also have to enforce ground contact constraints. So let's see how to enforce the safety constraints. So there's something called Nagumo's invariance principle, and it's as follows. Suppose I want to make sure that my state stays within the safe set. given by the 0 super level set of this barrier function b of x. So if I start within the set C, which is shown over here at the bottom, and I want to stay within it, the only thing that I need is when my state reaches the boundary, which is this ellipse, then I need to ensure that there exists a control input u that can make sure that b dot is greater than or equal to 0. So this will then keep b always positive, which will then keep my state within this. So this enforces that C is control invariant. The only problem with this is you're waiting until you reach the boundary, and then you need a huge control input to enforce b dot is greater than or equal to 0. We can make this process a little bit more smoother using control barrier functions that were introduced by Aaron Ames, Jesse Grizzle, and Paulo Tabudo. So the idea is, instead of looking at when b reaches 0, you're looking at the value of b at each instant in time and enforcing a constraint on b dot. So the idea here is I have an exponentially decaying function. So when b dot is equal to minus gamma b, as long as I can pick a u such that b dot is greater than minus gamma b, my b will evolve over this exponentially decaying function. So I'm now lower bounded by this decaying function. So then I can smoothly ensure that I'm always above b greater than or equal to 0. So the control barrier function formal definition, you need a continuous differentiable function whose gradient exists on the boundary and satisfies this particular condition, which basically means there exists a u that satisfies this, which then gives you this property.
Hi, Koushil, this is Barry. We wanted to suggest, can you just turn your computer audio down a little bit, because the videos are a little bit loud and we can't hear you when you talk over them.
Got it.
Thank you, sir. Sorry.
Okay, so going on. So we have a control barrier function. The idea is to design a controller that enforces this particular constraint. Now let's take a look at what we have. So we have the control Lyapunov function-based control, where we want to enforce this particular constraint. This guarantees v decays exponentially to 0. On the right, we have the control barrier function. And as long as we can enforce this particular constraint, b remains positive. Another way of looking at this is, on this, my state evolves in this green region. Here, my state evolves in this green region above the barrier. Very similar constraints. The only difference is the inequality sign. Now, in both cases, v dot and b dot are affine in my control input. So I can put these together in a quadratic program. Both these are linear constraints in u. This is the quadratic cost. So it becomes a QP. Okay, so we have all of this. So let's see this in action. So here's a legged robot. It's given a terrain of stepping stones that are stochastically placed. The robot can see only one step ahead, so it doesn't know the entire terrain. Under actuator system, with this controller, it basically changes the periodic orbit or deviates from the periodic orbit to ensure foot placements. Here's the same controller in action on a more complicated system. It's in 3D, and here the step length as well as the step width is changing. Now, if you combine it with multiple periodic orbits, and then you can do a lot more stochastic terrain. So here the step length, step height is changing, and you're getting precise foot placements. So we get this working in an experiment. So here the system has only one step ahead. The stepping stone is stochastic. So this is with multiple periodic orbits. You can also apply these controllers to other systems. So here's an example where you have simultaneous manual and autonomous control. So there's a human pilot who's trying to control this aerial system, but the controller is trying to keep you safe within this virtual boundary. So if it detects that you're going to collide, it smoothly takes away manual control and replaces it by a control that ensures safety. Okay, so a few quick advantages, disadvantages. You can apply these on high dimensional systems. You can apply this in real time since it's a quadratic program. You can also use this as a safety filter. So if I have a controller that I want to use, I can do the minimum deviation to enforce safety. You can combine it with other control approaches such as model predictive control. The main disadvantage is to synthesize a violate control barrier function. Typically what you see is you can pick a function that you want to enforce, and heuristically it works out. If your QP is feasible, then you have guarantees and safety. If your QP is infeasible, then you lose those guarantees. So you could run into problems with feasibility. All right, so we've looked at control Lyapunov functions, control barrier functions. Now let's see what happens when you have model uncertainty. So these are all model-based controllers. They work really well when you know the model. When you go to a physical system, even your best model is not the exact model for the hardware. So there's model discrepancies. Now there are robust and adaptive approaches for control Lyapunov functions and control barrier functions. They can be used for model uncertainty. I won't be going into those here. What we'll do is let's try out something else. Let's go all the way along this axis to a data-driven approach, completely data-driven. Let's throw away all the models and we'll use reinforcement learning. So model uncertainty, you have one particular model, but you have a nominal model on which you need to design your controller on. There's model uncertainty everywhere in the real world. The models that you have are uncertain. Your environment is uncertain. In fact, I would hypothesize that this was the main reason that many of these systems failed in the DARPA robotics challenge. You want to combine this model uncertainty with safety guarantees, and this becomes a really tricky problem. What do we do? So what we'll do is, we'll throw our hands up and we'll say, hopefully learning will help us here. So here's a problem that I threw at one of my students. And we're looking at whether we can use reinforcement learning entirely to solve this problem. Although, when we say we're throwing away the models, reinforcement learning is based on a simulator. The simulation uses models. So there is still some model in play. So this is joint work with Sergey Levin and Peter Rabin. So you've probably seen lots of reinforcement learning applied to dynamical systems in simulation. So here's a character. It can do all of these things, but there is no way this will work on real hardware. You're moving your joints really fast. There could be system delays. There could be measurement delays and so on. So a quick preview of our results. So here's a reinforcement learning based controller in action on CASI. You can see the robot walking backwards. It steps on this gantry, slips, and still recovers. Here's another experiment where you have a push recovery that's being demonstrated. So multiple pushes and the policy can still recover. All right, so let's look deeper into this and see what's happening underneath the hood. So we'll look at two things. So one is a model-based controller. So this is a hybrid zero dynamics based controller, a virtual constraint based controller that was initially developed at Michigan, and we built on top of this. And we'll go into more detail on this. The next is a learning-based control on CASI. The main thing over here is you have some reference motion coming in from some controller that gets added to a control policy. So the control policy is only providing you these deltas. What we want to see is, can we take away this and have the control policy provide everything to your robotic system? Okay, so let's look at this initial control that we had. So what we have here is a desired gate parameter, P, and this encodes things like forward velocity, lateral velocity, yaw velocity, step height, and so on. And we look at what is the current gate parameter from your gate, compare these two, and then extract a gate from a gate library. So gate library basically has a whole bunch of gates that are computed offline. And this gate library is combined with some gate regulator, which basically provides you a way to stabilize these gates on the 3D system. And this stabilizes the gate. Now, when you're doing step height as well, it turns out the gains are very different for different gates. So you need a gain scheduling. So you combine all of this, and you can see this in action in the figure over here. The problem is when you go to hardware, you need a lot of gain tuning, you need a lot of experiments. So we want to see if we can come up with some policy where we can do all of this offline and then deploy this on hardware in one shot. Okay, so this is our learning-based policy. So we still use the gate library, and we have a bunch of inputs to our network. And the network outputs the joint angles, which then goes to a low pass filter and simple PD control, which then outputs joint torque. So let's look at the inputs to the network. So you have the gate parameters, forward velocity, lateral velocity, and so on. You have the gate itself that's extracted from the gate library based on the desired gate parameter. Then you have the desired yaw angle, the yaw velocity. And then we have observations based on what the robot is doing. And this feedback is also critical. So what's happening over here is we're taking the output of the policy and feeding it back to the network. And this is very important because what it tells you is I'm taking this input and I'm taking this output, I'm feeding both of them to my network. So in some sense, the network is trying to find out what is the mapping from this input to this output and trying to adapt to changes. So you're sort of building an adaptation right in this policy. Okay, so the network itself runs at 30 Hertz. The controllers, the PD control runs at 2 kilohertz. And the way we train it, we use imitation learning. So this makes the reward engineering a lot less effort. So basically you have a reference motion coming in from the gate library. You have a simulation, you're looking at the deviation from this. And you have some term to minimize impacts with the ground, a term to minimize the amount of torque that's used in the robot. In order to do sim to real transfer, we're also doing domain randomization. So you have a bunch of different parameters on the robotic system. This includes the mass, the central mass location, the friction, it includes noise in your measurements, it includes communication delay. So you generate, so we're basically using PPO to train the network. And we're also doing this in a curriculum fashion. So essentially, instead of doing domain randomization all at once, you do a small fraction and slowly increase this. So if you do that, then your training is faster. Okay, so here's the process for sim to real transfer. So we do all of this training in a simulation environment, Mojoko. It incorporates lots of different properties, sensor noise, communication delay, that's really important for hardware. Once we're happy with the performance, then we test it out on a more high fidelity simulation model, which has actuation dynamics, a different contact model, that's probably more closer to reality. Once it works on this, we transfer to hardware. So this takes about 400 million samples, about 1 week of training. But if you do all of this right, it does work on hardware. So here's the very first experiment that we're trying to execute on the system. So here's Zongyu trying to control the system at the back. There's the operator. Both of them are pretty scared, and you'll see what happens. So we start, and the operator actually freaks out. He thinks there's something going wrong, and he shuts the power while it was actually working. So it's very surprising to see this work on the very first trail. So we can also compare this with what you would get from a hybrid zero dynamics-based control, the baseline. And we can see the RL policy does better in the form of these desired commands that are given that are actually feasible on the system. The blue here is what can be done by this model-based baseline. So we can improve this using learning. Now the reference motion is coming in from gates, but it could also come in from other kinds of motions. It could come in from animations. So here's a kinematic animation. So you're trying to do hopping. The reference motion can also come in from motion capture. So here's a running motion, and in simulation, we can transfer this to Cassie. Okay, so here's this in action. I was very surprised to actually see this work. I expected it's going to be a very hard problem to get this working on the real hardware. Step height, lateral velocities, you can walk forwards, backwards. It's also robust to perturbations. It's robust to ground variations. So very powerful. But you still lose something. And we'll talk about what you lose. And what you lose is essentially guarantees on stability, guarantees on safety. So where we are headed next is there a way we can recover. Is there a middle ground? Okay, so we've seen model-based approaches. We've seen one data-driven approach that's pretty powerful. The problem is, we lose guarantees. So is there a way we can combine the two? And towards this, we'll look at something where we look at reinforcement learning for control Lyapunov functions and control barrier functions. All right. So here's a system. Here's a nominal model of our system. So F tilde and G tilde are not equal to F and G. They're probably close, but depending on how much of model uncertainty you have, they could be different. What we want to do is we want to use a data-driven approach to compensate for these uncertainties. So the idea is we have a quadratic program-based controller using either CLFs or CBFs that uses the nominal model. And this controller is parameterized by the network weights. So it's getting in these additional parameters. And there's a combination of these two to give you the control input that gets applied on the plant. So we'll talk about what the alpha, theta, and beta, theta are. Okay, so this is what we had for control Lyapunov functions and control barrier functions. And we had this together in one optimization. The problem is when you have model uncertainty, V dot and B dot are very different from what the real values are. So a true V dot is a combination of the nominal V dot plus an uncertainty term. The uncertainty can be broken up into delta 1 plus delta 2 times U. So it's basically a finite U. So these delta 1 and delta 2 are unknown. If there was no model uncertainty, these two terms would be 0. So the goal is to design a network that can learn delta 1 and delta 2. So we'll create two different policies that outputs alpha and beta. And the goal is to drive this, our estimate of V dot, to the true V dot. And we'll assume that we have measurements of the true V dot. And we'll create a loss function that essentially minimizes the error between these two. And we can do a similar thing for the control barrier function. And you can combine these two things into one reward. And typically in experiments, we only can measure V. And we'll use numerical differentiation to estimate V dot and B dot. So here's a reward. So we have the loss from the Lyapunov function, loss from one or more multiple barrier functions. If you have any constraints, we can similarly create loss for the constraints. So here, these are constraints that depend on the model. And you put all of this together, so you get a control, which is an optimization, where our V dot is estimated through these network weights, thetas. and we can output a controller that can learn this model uncertainty. So here's one example. So we'll apply this on a model of rabbit. We'll increase the mass of all the links by a factor of 2. We'll try to enforce safety constraints for stepping stones. We'll try to enforce friction constraints. So we'll train with this particular model uncertainty, but we'll also test with a model uncertainty where we have just a mass of the central mass. So here's this working in simulation. So we're still able to walk while also ensuring that you're making foot placements. So this is with a combination of learning, Lyapunov functions, and barrier functions. And
Hi, Koushil, it's Barry again. Can you turn down the videos again or not talk over them just because they are coming through pretty loud again? Sorry. Just if it's any more video clips.
Okay, got it.
Sorry about that.
All right. So this works, but we still don't have the guarantees that we are looking for, in the sense that we are combining reinforcement learning with the CLFs and CBFs. But when you combine this, we can still not make a guarantee of the stability and the safety for the reason that we don't have guarantees on convergence for the learning. So we are looking for some way to make a guarantee. And towards this, we'll look at another approach of a data-driven policy. So we'll look at Gaussian process-based control barrier functions and control Lyapunov functions. And we'll create something called a second-order cone program. So using Gaussian process regression, we can make guarantees based on the mean and the variance of your regress parameters. Okay, so here's an overview. So what we want to enforce, so we'll look at control Lyapunov functions first. So we want to enforce that V dot is less than minus lambda V. There's an uncertainty in V dot. Uncertainty is given by this delta, which is a function of X and U. Our goal is to use Gaussian process regression to collect data to estimate this uncertainty delta. And what we'll do is we'll also use the structure of a control or of our model uncertainty. So the uncertainty is broken up into delta 1 plus delta 2 times U. So it's affine in U. So we'll do a regression which captures this affine structure. And to do this, we'll introduce the affine dot product kernel. So you're not learning delta 1 and delta 2 separately. You're learning delta, but you're trying to capture this affine structure. Now, once you do this, then we want to use the guarantees that come out of the Gaussian process regression. And we can make this guarantee that this uncertainty is less than or equal to mu star, which is the mean, plus some constant times the variance. And this is a probabilistic guarantee. So you can guarantee with some probability delta that this constraint is satisfied. And what's here on the left-hand side is the nominal V dot plus our estimated uncertainty, which is a probabilistic guarantee. So this would be enforced with a probabilistic guarantee of delta. And we can put this in a quadratic program. So that's where we're headed. So let's look at the details. So here's the original control Lyapunov function based optimization that we had. If I look at V dot, it's broken up into LFV plus LGV. But the true V dot is made up of the nominal V dot, which is LF tilde plus LG tilde V times U, plus this unknown terms. This uncertainty term delta is what we want to estimate. Okay, so we want to use Gaussian process regression to do this. So let's do a quick recap of what's happening here. So I want to estimate this function hedge using a kernel K. And the posterior prediction, the mean and the variance are given by this from Gaussian process regression. And we'll use these to estimate delta. So if I look at the delta, we talked about this being affine, and we can restructure this so that it's affine in terms of 1 and U, just to formulate it in this manner. And then we'll use these functions delta 1 and delta 2. And to generalize this, if I were to create this as y, and this would be some functions h. So I have h1, h2, all the way to hp. So here h1 is delta 1, h2 is delta 2. My general formulation is I want to estimate h, c, from measurements, noisy measurements, z of hc. And I know the h has a structure, and the structure that is affine in y. And the way we'll do this is by looking at kernels for each of the h1s, k1s, and we'll put these kernels into this compound kernel, which is the affine dot product kernel. So the kc is now a quadratic in terms of this y. And this is the affine dot product kernel. So if you do this, what you get is the mean that's coming in from the Gaussian process regression is affine in y, and the variance is quadratic in y. So we can use these properties when we construct a controller. Now remember, our y was this 1 in u, and this gives us our mean, which is affine in this 1 in u, and variance, which is quadratic in 1 u. Okay, so the key thing for this theorem is the error between the mean of our estimated value. So, the error between what we estimate and the mean is upper bounded by a constant times the variance. And this is the probabilistic guarantee. And we can guarantee with the probability 1 minus delta that the estimated value is between the mean minus some constant times the variance, and the mean plus a constant times the variance. And this constant depends on this probabilistic delta, or the probabilistic guarantee that we're making. Okay, so what we are interested in is the upper bound. So we want to make sure that v dot is less than some value, but we know v dot is less than this particular value. And we know this is true with a probability of 1 minus delta at least. So we can then put this into a quadratic program. So with the probability of at least 1 minus delta, we can enforce that this constraint is valid. So this, we can do it by putting in this particular constraint. So here's the Gaussian process-based CLF, formulated as a second order cone program. Our mean is affine in u. Our sigma star is quadratic in u. But this is sigma, so then you'll have a square root term. So in any case, this becomes a second order cone program. You can still solve this pretty fast with some of the new solvers. Okay, so let's see this in action on a simple example of an inverted pendulum. So here's an inverted pendulum. So we have some model uncertainty, and we'll compare this with a model-based controller and what we get. So if you look at if you assume that we know the true plant, then our control Lyapunov function has a performance given by this black dotted line. Our approach using the GPs to find out the model uncertainty actually gives you the same exact performance, which is very interesting. There's a small deviations over here. If I used the nominal model, then you'll have this performance given by the pink one. And turns out we can also combine this with a control barrier function. Now this leads to some problems. So you have two different constraints. You can relax this first constraint, but you can still not guarantee that this second order cone program will be feasible. So you need to do some feasibility analysis. Okay, so this was pretty interesting, but probably have like maybe 5 more minutes, so let's see what I can get to. So if I look at the CBF constraint that I'm trying to enforce, I have a few components. One is a nominal model. So this is the nominal B dot. And this is the B dot, this is the estimate of the uncertainty that's coming in through the Gaussian process regression. So there's a mean, there's a variance. And I want B dot to be greater than or equal to minus gamma B. So that's this one. So the mean term is affine, and U, the variance term is quadratic. You can formulate this as this. So if we define this entire part, so if you define these two and these third last term as VW times 1U, then you can combine this. And what we need is all those terms should be greater than what's coming in from this beta term. So this is what we need to enforce. So this is the prediction coming in from the variance, and this is everything else. And we want to come up with a feasibility guarantee to enforce this. So the feasibility now is determined by a trade-off between the growth of this prediction because of model uncertainty, because of the variance in your prediction, and how much controllability you have for the B. So it depends on LGB on one side and the size of the variance of your prediction. So based on this, you can come up with different conditions to check for feasibility. And in the end, all you have to do is to look for a single eigenvalue to make guarantees on feasibility. Okay, so we can look at this in an example. So here's an example of an adaptive cruise control. So you're trying to maintain a constant distance between the car ahead of you. So you want to avoid collisions. There's a simple model for the ego car, the car that's being driven with autonomous control. And you have constraints on the inputs. You want to maintain the desired velocity, which can be enforced to a CLF. You want to maintain a safety objective that your distance should be greater than this particular value. It's dependent on the velocity. So depending on the velocity, you want to maintain some distance. Okay, so there's some model uncertainty in the mass of the thing as well as the forces that are being generated. So with this GP, CBF, CLF, SOCP, we are able to recover the performance of the nominal controller if I knew the model and make up for the model uncertainty. So this is pretty powerful. In addition, I can also make guarantees of safety and stability in a probabilistic sense. So what we have is the following. On the left, I had a model-based control that made use of the model structure. So on the entire state space, I knew my model. Based on that, I can design controllers that can stabilize my system, ensure safety. On the right, I threw away the model and I can still get my system to work, but I lose guarantees on stability and safety. What I could do is I could take a middle ground. I know some components of the model, so that gives me some global structure that's not accurate, but I can make use of that global structure to provide one control input. I can use data then to understand the local structure of the dynamics, and I can combine both of them and provide guarantees on stability and safety in a probabilistic fashion. Okay, so in the last 1 minute, I want to quickly showcase maybe a few of the projects that are ongoing in our lab. So here at the bottom right, we're looking at combining legs with wheels. So Cassie riding on hovershoes. Bottom left, we are looking at locomotion and manipulation. So how do you juggle while you're standing? Top left, how do you combine locomotion and manipulation again? So you want to manipulate an object by locomoting on top of it. Top right, we are trying to combine human interaction with legged systems. So we've seen all these movies from Pixar where these characters on screen can generate emotions for people who are watching them. How do you incite an emotive response? And you can do this through motion in addition to cues. All right, so thanks everyone for listening, and I'll stop here and happy to have a discussion and answer questions.
All right, excellent. Thank you, Koushil. That was great. Thanks for the carefulness of the presentation and the detailed explanations. I want to introduce our guest panelist today, Scott Kindersma, who is a research scientist at Boston Dynamics, working with Atlas. And for those of you that have been following the series, Scott might not be new to you. He was a speaker about a year ago, I think June last year. And if you remember, he talked about using trajectory optimization techniques to get, I would summarize his talk as how do you get Atlas to do cool stuff. And within the last year, he has clearly delivered on the promise. I don't know if you've recently seen Boston Dynamics video where Atlas was dancing with some of his other robot colleagues. And Scott is behind some of that technology. So it's an honor to have Scott again here to sort of lead the first questions of this panel. Please, Scott.
Thanks, Alberto. Great talk, Koushil. So I thought I'd ask a couple perspective questions. And the first one is, what do you see as the sort of role for verification and like stability guarantees in robots as they sort of like go out into the wild? You know, do you view this as like mostly a useful lens for doing control design, or do you actually care about, you know, being able to verify the performance of robots? And if it's the latter, sort of how do you think about the practical scoping of that, right? There's on the one hand, things like, you know, adaptive cruise control, which seems like, yeah, there's probably some possibility to really get that thing to work in the wild. And on the other hand, there's maybe totally general mobile manipulators where, you know, saying something about guaranteed performance seems a little bit harder to wrap your head around. I don't know, what are your thoughts on that?
Yeah, so safety verification becomes a pretty critical, right, as these robotic systems interact with humans. So if you're following the Tesla news in the past few days, there's a lot of problems. If you can verify that your approach, your control algorithm can provide some guarantees, then you can use this in the real world. And you know, you see a lot of autonomous cars having problems where you cannot guarantee that your controller would work in real systems. So making guarantees is really important. Verifying them is also very important. But these are challenging problems. The more complicated your system, the more harder it is to design controllers to verify them. So there's still an open problem.
Yeah, that makes sense. Another just high-level question I had was, you know, you were in this pretty unique position of having done really great work on both ends of the spectrum that you showed in your slides, going from purely model-based techniques to heavily data-driven techniques, and now some things in the middle. I wonder if you were sort of tasked with taking Cassie or some other state-of-the-art robot and saying you have like the next year to produce the world's best walking controller. What would be the sort of set of tools that you'd think about drawing upon right now to do that? And I wonder if you think that your answer to that question might change in, say, 5 years.
Yeah, there's a tug of war, right, between model-based approaches and data-driven approaches. And even if you look at the communities, the control community and the learning community, you know, they're getting closer these days. So people are trying to work at the intersection. What's going to be the winner in 5 years? It depends on what you want. If you're looking for something that just works, either approach could do that for you. Maybe one of them would probably need more data. One of them probably would need some tuning. But if you also need guarantees, and I haven't seen any approach with just learning that provides this. And that's the case I'm trying to make, where you need some middle ground. And now our initial results, which uses Gaussian process, is also flawed to the extent that, you know, you can't scale it. And so if your system is low dimensional, great, we can make these guarantees. If it's high dimensional, then you run into scalability issues. You know, research community is headed to solve these problems. We don't have a solution yet. Does that answer your question? In 5 years, where are we going to be? Yeah, so I mean, I can only say this based on what we have seen. So if you look at the computer vision, there you had all kinds of features, you had some heuristics, they had geometric models. All of that has been replaced completely with data-driven techniques. Learning has replaced that. Will that happen in real systems? Yes, if the models get more complicated. But if you need to make guarantees, then the answer is no.
Yeah, I think that makes sense. Yeah, I'm sort of interested in this tension between, you know, the roughly the two ends of the spectrum in terms of like practical, like engineering value propositions, right? So at what point is a sort of turn crank data-driven approach actually going to produce performance that is, you know, superior to something you can produce with model-based control? Or at what point is the process by which you derive that controller, you know, a heck of a lot easier than what you would do with model-based control? And I think that's sort of, we're at this interesting point in history where maybe the answer is starting to shift from one direction to the other. And so I was just wondering, from your perspective, having worked in both areas, if you're kind of feeling that as well.
Yeah, so I think one thing to keep in mind is what is the effort on the designer in terms of time spent, as well as the data that's needed. So if you have a ton of data, you can throw this at a network and try to get it to work with the network. If you have less data, or if you have no data, then you have to make use of a model. But if you have a model structure, then it's good to make use of that structure and only learn things on stuff that you don't have a structure on. So it's a trade-off between the two. And it's also the time that's needed. So from what I've seen, if the task is simple, then you could probably do all of this in simulation and learning and get it to work on the hardware easily. If the task is hard, then actually the model-based controller would probably take a lot more effort if you have a hard dynamical system. If you have an easy dynamical system, then it might be easier for the model-based controller to work in hardware, whereas the sync-to-real is still a problem for learning-based approaches. If your task is hard, then maybe the learning one is a little bit quicker.
Yeah, makes sense. Who's better at hover shoes, you or Cassie?
It took me eight months to get on these hover shoes.
All right, I'll hand the baton over to some of our contributed questions.
Excellent, thanks, Scott. I think Ransalu, you're going next.
Yeah, okay. Okay, so we have a question from the audience from Mason Cotre. The question is, robust control Lyapunov functions can be used to ensure safety as long as the uncertainty is bounded, which would be reasonable assumption for an RL estimator. Has your group considered this direction?
Yeah, that's a good question. The answer is yes. So we actually have a bunch of papers that uses robust control with combination of control Lyapunov and control barrier functions. The key there is you need a bound on the model uncertainty, a maximum. If I know that bound, then I can make use of that bound. And when we design the controllers, that bound becomes a design parameter. I'm assuming the bound is this, and if so, here's the system working. But I don't know the bound for sure, and the bound is state dependent as well. So finding the bound is not easy.
Right. So which means like for instance, Cassie. So we can't say this is the bound. Like say for a given terrain and given environment, can we kind of like heuristically find that bound?
So you could find a very conservative bound, but if you want to push the bound, to the boundary, so that way the controller can make use of that, then it becomes harder.
Okay.
And you also have the problem with robust controls. Robust control by definition are conservative. They try to take the worst case into account.
Okay, great.
So at some point, it might be interesting to combine, all these different approaches: robust, adaptive, and learning-based.
Reyes, I think you have another question.
Hi, Koushil, thanks for the great talk. There's a bunch of interest from the audience about the hyperparameter tuning for the Gaussian process. What parts are offline and online? So I guess at a high level, what tips can you give people who are maybe trying the same thing? And then people are very curious how that relates to the uncertainty bounds that you just spoke to.
This is for the Gaussian process regression, right? So far we've just applied this in simulations. So everything is offline. So we haven't done any online. We're working towards deploying this on hardware, and we'll probably run into a lot of these issues. So if you're doing things offline, then you don't really care.
Yes, maybe I can ask a follow-up question about uncertainty and so on. So this is Luca. Koushil, thanks for the great talk. Very inspiring. I'm working on the perception side of things, right? So I don't work on control. I work more on the perception side of things. And when I look at these school videos, I also picture the robot trying to figure out how the environment looks like in a way to be effective, like moving across the environment. And my question is, in these mathematical models, where does the perception uncertainty factor in? Is it something that you can capture to the Gaussian model part? Is it something that is just ending up in the model uncertainty? Or how do perception failures essentially impact the framework that you're proposing?
Yeah, I mean, one thing we've been thinking about, or we've done some work on, is using perception to find these stepping stones. So the perception can find your stepping stone and give you an estimate of where the next stepping stone is in terms of step length, and the controller will do a great job. If the perception fails and gives you a wrong estimate, then the controller assumes that the estimate that you got is correct, and it gives you safety guarantees on that wrong estimate, and it fails. So we've been working only on safety critical control so far. And what we need to do when we go into the real world is we have to combine it with perception. So we have to create a framework of safety critical perception as well, which we currently don't have.
So I guess you can still tolerate, as a small bounded uncertainty. The issue is that if the estimate is completely off, I guess that's the main issue, right?
So if you can provide bounds on your estimate from perception, you can take that as measurement bounds, and we can put that into the controller. So that's possible.
Got it.
The problem is we cannot guarantee those bounds. So I've been looking at approaches, whether we can use some neural networks to provide those bounds. And that's also an open problem.
Indeed. Thanks.
So I have a bit of a follow-up question building off of this uncertainty discussion. Everything that I believe that you've shown, the trajectory generation for the controller to track is done offline, correct?
That's correct.
And, all right. So do you have any ideas on how to move that online, especially once you start incorporating perception and the robot needs to respond to stuff around it? And ideally, is there a way to do that while baking the uncertainty into not just the controller, but the trajectory planning? So the trajectory planner should know something about how well the controller will behave.
Okay, I mean, so this can be done to some extent. So you're getting this dynamically feasible gates offline. And these gates correspond to walking forwards, walking sideways, maybe doing a jump, and so on. What you want to do online is you want to compose these gates depending on the environment that you see. And composing those gates online is feasible. Generating those gates online, also I've seen some work from Ionga Herod at Oregon, Ohio State. So he's doing some good optimizations of these constrained dynamical systems online, where you can generate periodic orbits within a minute or so. So I think going forward, it should be possible to generate dynamically feasible gates online. Whether you need it or not, I'm not sure yet.
Okay, so we have another question from the audience, and it's anonymous. So in safety, although violation of safety set is not allowed, the restriction of the set is also not desired. Have you ever studied the way to maximize the safe set region while maintaining safety?
So, if I understand the question properly, I think they want to generate the largest safe set and stay within that safe set.
Yeah. So, yeah.
Okay. Yeah. So the safe sets are defined by the barrier functions. So given the barrier function, the safe set is a set of all states where b of x is greater than 0. And the problem is coming up with the barrier function. So typically what we do is we pick some function that we want to ensure is positive, and we consider that itself has a barrier function. And that's a heuristic because we don't have a guarantee that that's a valid control barrier function. So you could test these things out in simulation earlier to come up with a valid CBF. Maybe you could use things like SOS, just the way you could extract Lyapunov functions. So you have to search for these valid CBFs.
Okay, great.
Koushil, I have a question. I wanted to go back to the beginning of your talk. If I remember, you start by showing us the affine equation, dynamic equation of motion of the system that you want to control. And you said lots of systems sort of fit within that assumption that there's some kind of affine dynamic equation. Can you help us parse that a bit more? Like, do you have examples of systems that would not fit into that category, that for which we would have to do something essentially different?
Okay, so yeah, so we assumed our dynamics is control affine, and under those assumption, your V dot is control affine, B dot is control affine. The controllers that you create are then put linear constraints on U, and the optimization then becomes a quadratic program. If your dynamics is not control affine, then these constraints on V dot and B dot are no longer linear in U. So you no longer have a QP, but you have some nonlinear optimization. If you can solve that nonlinear optimization in real time, you can deploy them on hardware. So the theory is fine, it still holds. It's just your implementation would then be dependent on the computation capabilities that we have. There are systems that are not control affine. Simple examples could be quadrotors. So depending on how you model the system, it won't be control affine. Because yeah, that could be the simplest example.
Okay, what do you do then for a system like that? Do we know, or I don't know?
Yeah, I mean, the theory is completely fine. There's nothing that breaks in the theory. What you could do is you could change where your actuation is. So for example, if I assume a quadrotor is actuated not by moments, but it's actually actuated by velocity, then it becomes a control affine problem. And you could use that as a QP, and then you have another controller that goes from the velocity to the motor torques. That could be one approach.
Makes
there are
sense.
a lot of systems that are not control affine. So I don't want to make the claim that everything is control affine. But yeah, most systems that we work with are quadrotor. I need to check one more time.
No, I mean, I think that it is definitely something that it's always present in sort of analysis in engineering systems, right? So there are problems that we know how to solve, and then there are problems that we would like to solve, and it's sort of at that intersection that we are sort of interested in working. So it's good. I think that it is useful to understand when the assumptions break and when sort of the math becomes more complex. Cool.
I think there's one more issue. I think the quadrotor is actually control affine. It's just that the Lie derivative corresponding to G is I mean, that's probably to do with the, no, LGV is fine. So that's fine. That's a problem with the IO linearization. So that's a different thing.
Okay, I think, is it Shreyas that you have the next question? Cool.
Yep. So there's a fun audience question. which is your favorite legged robot by either its algorithm or mechanical implementation? And more precisely, I would guess, which is the most control affine legged robot you've worked with, since you showed us so many different videos.
So which is the most fun robot I've worked with? Okay, so.
And I guess also, why does it impress you?
Okay, so the ones I worked with, so that makes the set of robots very small. I worked with a bunch of them, but they're still small, so that way I don't have to think too much. Yeah, so I got acquainted with Jonathan Hurst during my PhD. Probably the wrong thing to do, because he loves making robots. And then I get to work with all the robots that he makes, and he makes too many robots. So he's created the Mabel, the Atreus, and Cassie, and each robot that he makes is more complicated than the previous one. So then you end up spending more time, you end up losing more hair. So life is hard. But I think these systems are really good. So the one that I work with currently is the one that's the best, but then it keeps changing as a new robot comes out. And he's got a new one called Digit that's out.
Maybe I want to follow up on that and ask a little bit of a higher level question. So we have Scott here, and of course we are all aware that there is a lot of excellent work, especially on this topic, coming from industry, in which this typically can leverage a little bit more resources, more data, and so on. So Koushil, the question for you is, what do you think is the best way for academia to engage with industry? What is a healthy format for a collaboration in which both industry and academia can benefit from each other?
Okay, so this is I guess in some sense, political question, but I'll answer it anyway. Okay, so I think one way it's easy to engage. For us to engage with the industry is probably easy. The other way is a little harder for the industry. And we have workshops, we have conferences, the industries, they can come in at any time. All you have to do is register for the conference or for the workshop, drop in for a talk. So the industry, if they want, they can be on top of the state of the art that's going on in the university. The other way is really hard. I have no clue what Boston Dynamics does internally. I have no clue what any of the other legged systems, legged robotic companies do for their approaches. For instance, Agility Robotics or maybe Unitree. What are their control algorithms? They're all trade secrets. It makes sense. But I think it's in the best interest for the research community as a whole to put out our papers, to put out our work, so we can build off each other and we can make scientific progress. So we can go further, we can create more things, we can come up with more creative algorithms.
And that, by the way, is also for, in the long term, is also an industrial interest, right? Because if the community is reinventing the wheel, if the robotics community or the academic community is reinventing the wheel, I don't think that's beneficial in the long term anyways, right?
Yeah, that's true, yeah.
Yeah, I mean, I think that there's there is always this balancing act between companies wanting to share the work that they're doing back with the community that they're learning so much from. I think there's actually value to be had in doing that in terms of recruiting, getting people excited about, coming to work with you and things like that. But you have to balance that with, protecting the intellectual property that you're hoping to profit from, ultimately. But I think we could, help with that last point that Luca pointed out, which is we could do a better job about communicating the problems that we think are exciting, that we think are hard to solve. And that could give some high-level direction to people who are, actually doing state-of-the-art research and publishing it. So I think we could do a better job in how we're communicating in both directions, and work around some of the limitations that we have.
Thanks, guys. Great inputs.
Wanted to ask another question, Koushil. So you mentioned your relationship with Jonathan and how he has been handing you challenges to address and control problems. I wanted to hear your perspective if you ever go back to Jonathan, or I'm thinking of Jonathan as the hardware person, right? Or with suggestions saying, hey, it would be great if this robot, if this machine had I don't know, were to be different in these ways, or had more power in this joint, or had, I don't know, the more less latency in this communication, or so that there's sort of some feedback to whoever is building the machine, so that, for example, is more controllable. Do you ever close the loop in that sense?
Yeah, so I think if you look back, most of the designs for the mechanics and for the control have been done independently. So someone designs a robot, they gives you the control person, and the control people, maybe they curse the person who designed, saying, oh, you made this so hard, but yet you design a controller to make it work, and then things are fine. The ideal thing is to collaboratively work on it together. And this is what happens to some extent in the aircraft industry. So you're creating fighter jets that are very agile, but are still really unstable. And that gives you the agility. So you're right at the razor edge on balancing this. And this can come up only when you combine the design and the control authority of that design, at least for fighter jets, for instance. So something similar should exist for the legged robots. I've spoken with Jonathan after each of his robot. I think maybe after Mabel, I gave him a whole bunch of suggestions. And some of them get incorporated, some of them don't, because from a mechanical design perspective, it's very different, right? What you see. I don't do robot design. I don't have much experience. So things are different. But I think it'd be good to combine all of this.
Yeah, I don't know.
Sorry, companies that are vertically integrated, for instance, like Boston Dynamics, are probably already doing this to a large extent.
Yeah, I don't know if you want to comment on that, Scott. What's your perspective?
Yeah, I mean, we're very tightly integrated between our mechanical, electrical design and controls teams, and it's an iterative process to produce things that are high performing. You can't just design it and hand it off and then hope for the best. It's we're constantly upgrading things and thinking about how we can do things better.
Yeah, unfortunately, I don't have that luxury.
But maybe it's worth thinking, like, what can we do in the research community so that to improve that sort of flow or that communication? I don't know if you have ideas or have you thought about that?
Yeah, I think you need people who are working at the intersection of the two, and only they can make some good research progress on this. Or you need some strong collaborations. There are tight collaborations between mechanical designers, control designers. And you could also probably combine that with perception as well, right? Sensor locations, sensor. As you start to commercialize this technology, you would want to decide on what sensors to use, how much to spend, can you get away with low cost sensors? In a similar fashion, can you get away with low cost actuators and still get the same performance? Sangway is probably getting closer to this with the mini cheetah, for instance. He's also doing some of that. I think Boston Dynamics will probably do a lot of this as they start to commercialize. They're probably already commercializing. Internally, Agility Robotics is probably doing some of it, I think. For a single person in the research community working on one field, it might be hard to do it. Yeah, do you design, Alberto?
I mean, no. I mean,
you probably do
by definition, we don't design. That doesn't mean that we don't try, but but it's not the thing that we do.
It could be similar things in manipulation as well.
Yeah, definitely. Excellent. I don't know if there was any other questions, Gonzalo.
Yeah, I can hop in and ask one question. So this is a question from Murad. This kind of more inspired from Murad's question. So like, if whenever we want to run all these robots in the real world, we need actually like real-time performance, right? So his question is more about like how much of your work addresses time delays. So for instance, when we use GPs, maybe although they provide all uncertainty bounds and all safety guarantees, they can sometimes be slow, right? So like how much of what you have worked actually addresses this kind of like the trade-off between speed and accuracy and safety, and what would be like the future trajectory?
Okay, I think time delay is really important. Time delay changes your feedback, could change your feedback from a negative feedback to a positive feedback. So it could destabilize your system. So it's really critical. If we take a controller with a large time delay and we put it on a system, things start vibrating, there's large vibrations, you run into problems. So we know when our computation is slow because it fails. Are we incorporating some mechanism in the control design to address this? Right now, no. But we do it by a, I guess, trial and error approach. So we try to optimize our computations so that we can get things computed within the real-time hard limit constraints. And what those constraints are dependent on the agility of your system.
All right, I think it's thanks for the question and answer. I think it's a great time, to close. So I want to thank everyone for contributing to a great discussion. And I would like to close this event by thanking again our speaker, Koushil Sreenath, for the amazing talk, our guest panelist, Scott Kindersma, and thank you all for tuning in. So the next Robotics Today seminar is going to be in May. In the meanwhile, stay safe and see you next time.